All right, so I just want to go back and record what we talked about in class today from that very first exploration, the one about accumulation from a table. Remember, this is, I don't know what all that is. Sorry. This is the one where I asked you to recreate the table to find position, but using average speed over the time interval. So here's the table that I had you do for homework, and we checked it. Remember, for velocity, you were finding the average speed over the time interval. So like from time 7:30 to 7:45, you were using 28 and 25 and you were finding the average. So 28 plus 25 and then divide by 2, your average speed is 26.5. So that when you found the distance traveled during that time interval, you took that speed, that average speed, and you multiplied it by the change in time, which is just the 0.25, okay? And then you found the next average speed and you multiplied that by 0.25, because again, you had only gone 15 minutes, which is a quarter of an hour. All right. And so then to get the position, how far are you from port? All right. You just add that distance that you traveled to your previous position. And so our table showed us that we, at the end at 9:15, we were 143 miles from port. Okay, and then we talked about how this was a little bit better of an approximation, because using average speed technically created a trapezoid, right, in terms of shapes to estimate the area. Let me change colors. Under, like, from one position to the other. So what we did was we said, okay, we took the speed from time 0 and the speed from sorry, not time 0, but, or you could say it like that, from 7:30, and then the speed at 7:45, and we averaged them together, and that actually created a trapezoid. All right, and so when we found that average of the speed at the beginning and the speed at the end, right? So we added them up, we divided by 2, then we multiplied it by the 0.25 to get the distance. The distance ended up equaling the area of all of these blocks. If I counted blocks and then tried to estimate how much was in this little section here, we would get roughly, I mean, it would be hard to get exactly 6.625, but that is mathematically what you would get if you did the trapezoid here. Okay, so again, counting blocks, it would be hard to get 6.625, that's pretty accurate, but using the trapezoid formula, which is essentially the average velocity times this little bit of time here, we could get the area of a trapezoid. And then we basically, each distance that we found was the area of the next trapezoid. And if you add them all up, you got the distance that you were from port. Okay. And so then I talked about how that distance is a position. And so if, you know, we're typically talking about velocity, a lot of times we say that position is x of t. And so earlier in our notes the other day and in the previous video, we had said x of t was equal to 110, because that was our starting position, plus the sum of all of our distances. And remember, distance was the velocity, whether we use the beginning velocity or the average velocity, times the change in time. So delta t equals the change in time, or the time increment, okay? And so that was 15 minutes, but that's 0.25 of an hour, okay? And if you add all of them up from time 0 to time 1.75, then that's how we got the ending position. Okay, well, each of these time increments were 15 minutes. But what if I made those time increments smaller? Okay, do you think I would get a more accurate answer? I hope so, because again, this is just approximation. Well, in calculus, if you make those time increments so infinitely small, okay, if I make the time increments infinitely, oh, that's supposed to say tiny, I guess, but I certainly didn't spell that right. So those time increments are so tiny, we call that a definite integral, and we can change our notation. Okay, so our time increments, if we make them infinitely tiny, instead of writing it as a sum, we can change it into this thing called a definite integral. All right, and the integral symbol just looks like a really tall, skinny S. All right, and instead of putting time 0 on the bottom of a sum and 1.75 on the top, we put those are called bounds of our integral. So we put 0 on the bottom, 1.75 on top. And instead of doing delta t times v of t, the v of t is still what we're technically integrating, but delta t is represented as dt. So it still kind of stands for the change in time. All right, so again, we call that a definite integral. And actually what it gives us is, instead of an approximation of the area, it is the exact area under a curve. And it's really just the sum of an infinite set of products. So it is a sum, but it's an infinite set as opposed to just you know, a few particular increments of time. Okay, and so then what we did was we said, okay, so what we've essentially done is we've said our position is equal to 110 plus, and again, we approximated this, but the definite integral from 0 to 1.75 of v of t was approximately 143, okay? And so we used trapezoids to get that approximation, all right? Now 110 was our starting position, and so technically the definite integral part is only equal to, or is equivalent to the 33, because we started at 110, so the integral part is only equal to 33, but what that really is it's the area. All right, so if I go back up here to my picture and I drew trapezoids from every single piece, all right, and then I counted up all the blocks under, all right, under those trapezoids all the way from 0 to 1.75, I would get 33, or approximately 33 total blocks for all of this space, okay? And so that is an approximation for the exact area, all right? And when we learn how to actually find an integral, you will be finding the exact area. So these trapezoids were just, they were just an approximation for that area, okay? Then, so then we said, okay, so essentially I kind of wrote it in terms of standard notation. If our interval, our time interval went from 0 to 1.75, that could be any interval, all right? So that we just say A to B. And if our function is velocity, all right, so if we integrate velocity, we actually get position, x, right, the function x, but it's a definite integral, so you are required to get displacement, which is going to be your end position. So the position with the end of the interval plugged in minus the position with the beginning of the interval plugged in. Okay, so x of b represents the end position, x of a represents the beginning position. So remember, this is displacement. And so like, think about why that works. Okay, think about why that works. All right. Think about our connection between velocity and position that we've learned in the past. Okay, if you take the derivative of position, you get velocity. And so what happens is, like, what this mathematical operation does, if you integrate velocity, it actually takes you back to position, right? So they undo each other, basically. Integrating completely undoes, for lack of a better word, differentiation. So you will hear the term anti-differentiation. So integrating is the same thing as anti-differentiating, okay? And then we took it one step further. Instead of calling it v of t, we just said the derivative of x, all right, of t. So yes, that's position, but that could really be any function, okay? I didn't put this in class, but we could even say it could be, well, not 0, from a to b, all right, of f prime of x dx, okay? So just a generic function. If I have the derivative of it and I want to integrate it over an interval from a to b, so this is called a definite integral, it will take me back to the original function evaluated at the end of the interval minus the beginning of the interval, okay? And so that, again, is the fundamental theorem of calculus, and that is something that you need to familiarize yourself with. We will be using that from now on quite a bit, okay? All right, and so that actually ended that first exploration, and then we started, oh no, it didn't, I apologize, shame on me. I had you start looking at number 2, and I asked you to finish it on your own, so let's just refresh real quick what you were doing here. We had the velocity of a car in feet per second, traveling on a straight road, 0 to 50 seconds. It's given in the following table. Estimate with a trapezoidal sum the distance the car traveled in 50 seconds using the intervals indicated by the table. So this time we don't have, we're not actually drawing a picture of it, but we are essentially creating trapezoids, which is the same thing as average velocity, okay? Which means we're using the time increments indicated in the table, so from 0 to 15, 15 to 25, 25 to 45, and 45 to 50. And we need to get their average velocity, all right? And so that's the velocity at the beginning of that particular interval plus the velocity at the end of that interval divided by 2. That's how you get an average. And that's really how you get the area of a trapezoid, right? And then, well, that's the 1/2 b1 plus b2, all right? But then you need to multiply it by the time increment, which is literally how long is it from 0 to 15? That's 15 seconds, okay? And then you do it again for the next interval, and I wanted you to finish that out. And then just understand that even though I wrote it in terms of v of 0 plus v of 15, I'm literally using the 0 and the 30 from the table, okay, and then the 30 and the 70, and then I'd be using the 70 and the 60 and so on. So I wanted you to finish that up and then understand that your answer is an approximation, okay, of this integral, okay? Your answer is an approximation of this integral, okay? And if I use the the fundamental theorem of calculus, I'm essentially saying that if I integrate velocity from 0 to 50, I get the position at 50 minus the position at 0, right, which is displacement. And so you should end up with 2,355. So I do hope you go back and finish that. And then we completely talked through number 3 because we didn't use trapezoids, okay? We were talking about this female pilot, and she's coming in for a landing on an aircraft carrier, and we're given her speed, all right, as she comes in for a landing until she comes to a stop. And I want to know how far, right, what's the distance how far her plane travels as she comes to a stop. How far does it take her to actually stop? All right, and then later we wanted to look at, is her plane in danger of running off the other end of the 800-foot long flight deck, and can we justify that? So because we were thinking ahead, we said, okay, well, if we don't want her to run off the flight deck, even though a trapezoid is a good approximation, we almost want to over approximate how much space she needs. And so we said, okay, well, if we want to over approximate, and look, her rate is decreasing because she's slowing down, right? So if we want to over approximate a decreasing velocity, all right, we should probably use the higher velocities, right? So the velocity at the beginning of each time increment, Okay, so we're approximating her total distance. All right, so we're approximating the integral from time 0 to 3 seconds. All right, by setting up basically rectangles, okay, where we're taking the velocity at the beginning of a time interval, right? So v of 0 would be 300, but then we're multiplying it by the time increment for that interval. Okay, so we're using the velocity at the beginning of the interval, but we're multiplying it by the time increment. And since each one of these time increments were different, we had to break it up into several pieces. So it's the velocity, which in the first one is 300 times the time increment 0.6. Then the second velocity was 230, and that time increment was 0.9, and so on and so on. And so we actually finished this one in class, and we ended up with approximately 515 feet. So we're saying, and remember, we over approximated, she needs about 515 feet in order to land. So we wanted to know, was her plane in danger of running off the other end? And since the flight deck is 800 feet long, it's more than likely not going to run off the end unless for some reason she doesn't land, she doesn't actually touch down, right, within the first 285 feet, okay? So as long as she gives herself 515 feet, she should be good, okay? And that wrapped up the first exploration. So that'll end our video here.